Hi everybody, we're starting chapter 4 with 4.1 linearization. Everything about chapter 4 is taking what we learned in chapter 3 and applying it in different ways. So in this section, the main goal is to take a look at how can the derivative, or specifically the equation of the tangent line, allow us to approximate a function value at a point that's close to where the tangent line is located. Okay, so we're going to warm up with just finding the equation of the tangent line to this equation at the given point. So remember, anytime we're coming up with a tangent line, we're looking to find the point, the slope, and then the line. So in this case, the point is given as 1, 0. Our slope we derive implicitly, so 2x plus cosine y dy over dx equals, here we have a product rule, so x derives to 1, y squared stays, plus x stays, y squared derives to 2y, dy over dx, and the 1 goes to 0. Okay. My next step is to isolate the dy over dx. So I'm moving my dy dx terms to the left, my non-dy dx terms to the right, and factoring. And then finally dividing by that cosine y minus 2xy. Okay, at this point that I can plug in the point 1, 0, so that I have my slope at that moment. And I would have an answer of -2 for my slope. So my equation of the tangent line is y minus 0 equals -2 times quantity x minus 1. And that tangent line would allow me to approximate values that are very, very close to this point for the given equation. All right, so in order to investigate this idea of linearization a little bit more, I want to bring back what is the limit definition of the derivative. So back in the beginning of chapter 3, we defined f prime of a as equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. Okay, which is essentially the same thing as saying the limit as delta x approaches 0 of f of a plus delta x minus f of a divided by a delta x. Right? If that delta x is extremely small, this is equivalent to limit as delta x approaches 0 of change in f over change in x. Right? So this is true if and only if delta x is very, very small. Now, this idea of very small is, of course, relative, dependent upon the function, the numbers that we're already looking at. So there's no way to define what very small means. It's all relative to the exact problem. But we're able to say, based on this, that the derivative at a is approximately equal to change in f over change in x, based on our limit definition, right? That's what we've been doing. And therefore, if we want to know just how much of a difference are the function values, then we can say that change in f is approximately equal to our derivative multiplied by that change in x. Okay. And that allows us to approximate the difference between one function value and the next relatively easily. So here's our steps. Identify the function, identify the a value and the delta x, and then apply the linear approximation. So sometimes examples are given to us like this, where a function is not clearly defined. We're not even totally sure what they're asking perhaps, but without a calculator, can we approximate what this expression would equal? 1 divided by 10.2 minus 1/10. So again, we have to identify the function. So based on how this is written, what's the operation of the function is what the question is really asking. I would say that the function is 1 over x, 1 over some value, or x to the negative 1. And the number that we appear to be approximating with is a is equal to 10. That's the nice easy number that I'm extracting from there. And therefore my change in x, my change in value, is 0.2 or 2/10. Okay, so I've got all of the information that I need, and then that linear approximation, we need to know what the derivative is at that specific moment so that we can come up with our linear approximation. So I need to know the derivative of the function, and that would be negative x to the negative second, or negative 1 over x squared. I need to specifically know this at 10, so negative 1 over 10 squared, or negative 1 over 100. And then I can figure out that the change in f, right, the change in that function value, the difference between them, is approximately equal to that derivative, right, which is slope, which is change in f over change in x, technically, multiplied by the change in x, 2/10. Right? If I'm taking change in f over change in x approximately, and I'm multiplying it by change in x, then I'm canceling out and I'm approximating that difference. That's what's happening here with this linear approximation. And this is equivalent to negative 1 over 500, which is a really small fraction. And therefore, if I used 1/10 as my approximation for 1 over 10.2, I'd be pretty close to the right answer. Okay, so here's another question just like this. How much larger is the cubed root of 8.1 than the cubed root of 8.2, which of course is equal to 2. So we're looking for the change in f between those two. Right? It's the same thing as saying change in f in a little bit more complicated notation of f of a plus some delta x minus f of a. So that's equal in this problem to the cubed root of 8 plus 1/10 minus the cubed root of 8. Right, so now I can easily see a function. That function would be the cubed root of x. I have that nice easy value that I would be able to do mentally, and that's 8. And I can see the change in my x's is that 0.1 or 1/10. Okay, so in order to do my linear approximation, I need the derivative. And I'm thinking of this as x to the 1/3 when I'm deriving, so 1/3 x to the negative 2/3. And then I need to evaluate this at 8. Which is 1/3. And when I'm doing 8 to the negative 2/3, the cubed root of 8 is 2. 2 to the negative second is 1 over 2 squared, or 1/4. So I get 1/12 there. So therefore my change in f is approximately equal to 1/12 times 1/10, or 1 over 120. Okay, so I'm going to leave this one for you to do, and we can go over it in class. And we'll take a look at this one together. So thermal expansion. A thin metal cable has length L equals 12 centimeters when the temperature T is 21 degrees Celsius. Estimate the change in length when T rises to 24 degrees Celsius. Assuming that the change in L over the change in T, dL over dt, is equal to K times L, where K is equal to 1.7 times 10 to the negative 5th Celsius to the negative 1st. And K is known as, or called, the coefficient of thermal expansion. So, organizing our thoughts here. Our goal is to figure out what's this change in L, what's the change in length, and that's approximately equal to the derivative when L is 12 multiplied by our change in T. So that's the information that we need to have. We're given the derivative, right? We're given the derivative. We know what K is. We would then plug in the L, which is given. We need to figure out what is the change in T. Well, we want to know between 21 and 24. So therefore, the change in T is 3 degrees Celsius. So this is approximately equal to 1.7 times 10 to the negative fifth times 12 times 3. And the units, which I didn't write in here, but I would have the K is the C to the negative 1, canceling out the C for my change in T. So those units are gone, and I would be left with just the centimeters from that 12. So I went to a calculator for this one. But you wouldn't have to, right? I could do on this side, I could do 12 times 17 and move my decimals around. Or really, 12 times 36. But anyways, if I did that on the side, 12, 17, I would get 84, bring down a 0, 2, and 1. So we get 204, right? I have to put the decimal back in. It would be 20.4. Now I'm multiplying by 3, and that's where I would get a 61.2. So you could still do this without a calculator. 61.2 times 10 to the negative fifth centimeters. And then rewrite, of course, proper scientific notation, 6.12 times 10 to the negative fourth centimeters. So that is how much this changes when the temperature rises 3 degrees. All right, I will leave this example for us to do in class. It's very similar. It's talking about how much does the size of the pizza change. Okay. All right, now here's the other extension of this linearization model. So what if we wanted to actually approximate a function value rather than just that change? So here we're going to use the equation of the tangent line. So this is no different than what we've been doing. That's why I chose the warm-up that I did here. So approximating f of x by its linearization. So when we say linearization, it's simply the tangent line, and we're using that tangent line as an approximation. And we can use this as long as we're picking a value that's close to that a value. Okay, so in that pink highlighted box, f of x is approximately equal to the linearization L of x, which is equal to f prime of a, there's our slope, our derivative, times x minus a, plus f of a. So our tangent line typically just has this over here with subtraction. That's the y value. Okay, so nothing really is different. So compute the linearization of the function given at a is equal to 1. So we need our point, we need our slope, and then we can get our line. And we're getting them in the same ways. All right, so our point's coming from the original function, so we need to know what's f of 1. So square root of 1 times e to the 1 minus 1, or e to the 0, and that's equal to 1. So our point is 1 comma 1. Our slope, the derivative using product rule. Let me erase this line because I'm going to end up squishing myself in here. Okay, so the derivative here, root x, would derive to 1/2 x to the negative 1/2. E to the x minus 1 stays, plus root x. E to the x minus 1 derives to e to the x minus 1 times a 1 for the inner prime, so we don't really need that. So f prime at 1 would be 1/2 times 1 plus 1 times 1, which is equal to 3/2. So y which is equal to L of x, is equal to 3/2 times quantity x minus 1 plus 1. So I could use this model to plug in like 1.1, and that would give me an approximation of what that function value would be. Okay, so here we go. Here's a table of values actually to fit this, where we have our approximation, our linearization, which we just found. So if I did use 1.1 and I plugged it in, my calculator would give me this answer. My approximation would give me this answer. So we're really, really close. Our error is very small. If I use 0.999, there's my linearization. There's my calculator. Pretty close. But if I went to 2.5, so that's where we're not close enough anymore, the linearization gives me 3.25. The calculator gives me 7.086. So not effective there. Okay. So we'll do one more together, and I'll leave the last one for us to do in class. So find the linearization at x equals a. So the function is x squared over x minus 3, and a is equal to 4. So I need my point, which means I'm just evaluating at 4. So I would have g of 4 is equaling to 16 over 1. So my point is 4, 16. I need my slope, so I'm using quotient rule and getting 2x times x minus 3 minus x squared times 1 over x minus 3 quantity squared. And I'm evaluating this at 4. So that would be 8 times 1 minus 16 times 1 over 1. So that is a negative 8 slope. Point, go to the line. So L of x is equal to negative 8 times x minus 4 plus